Hello, good morning, everyone. We will start soon. Good to see you all. We are going to continue the discussion we started last time and start a new topic. I know I was a bit fast last time, so I want to make sure that we get a little bit of time to finish the lab session we started on decision trees and random forests. And the topic that I was eager to start this week will be started today. I hope you have had enough sleep. It is quite possible that you were all up late yesterday, and we all need to be patient and find out what is going to happen, but I appreciate that. And so thanks for making it, and stay focused today on what we will do in this class and everything else that is going to happen. I'm going to be doing a few things today, right? So we will finish a lab session, which means I will be going out of this display now and go to an R studio, and then I'll come back and do lectures. And for the lectures, I would have another one. So we'll have to switch between screen sharing in 3 different ways. And so be patient with that. But I wanted to start off by telling you what we will do today and a few other, reminders and recaps. But let's do the usual thing and start with a warm-up question. And today's warm-up question, I'm going to ask Ailia to type it. And I'm going to take you back to a time when you would play card game or board game. And I'm going to ask you what your favorite card or board game is. So by card game, I mean like Go Fish counts. And by board game, I mean things like Monopoly counts. So whatever it is, tell me what your favorite card game or board game is. And that's our warm-up question for the day. And Ailia would type it and we will get started. And what I want to do with this slide that I told you that we'll be switching is to first have a few things. These are probably things that you are thinking about, and I want to make sure that you have them all in one slide. First, everybody has submitted all assignment 5. The last assignment in terms of assignments is in. Helen will be grading them. As you know, as you've gone through it, it is a fairly large one, so it will probably take a little bit of time for her to complete. So that's completed. All is left is for Helen to grade. Those of you who are doing 575 I have asked you to give me your proposals for survey paper topic, and that is in. And I will be the one to do that. And there will be 1 of 2 responses. Go ahead or change it this way. I have started looking, but I want to always make sure that I go through them before I get back to you. So watch out for responses on Blackboard on my go, no go decision. One thing that I have seen from what I have seen so far is the ones that I have seen are good choices. When I have something else to suggest, it is just because of scope or something. It's not anything else. So there was a good guidance that you got, and I'm sure you have your own interests and you want to make the best out of it. So whatever you suggest would also make sense. So my default position is to go with what you suggest. Only when I see something that is unhelpful, then I would suggest, or not fruitful, I would suggest another thing. So you have done that. You will hear from me. And the next thing about that paper is going to be the one when you submit. There is no other interaction between you and me when it comes to survey paper. And this is the place where 475 students would, just for a second, close your ears, and I'm done with that one now. The project progress report was something that we talked about. I have had many good meetings with many of you, and some of you have had follow-up. If you remember, today, midnight, would have been where I have said, tell me where you are. First, relax. This is a progress report. What it means is you tell me where you are. I don't expect people to have results. If you have, wonderful. If not, it's perfectly understandable. But I just want to know where you are. Meetings you have had, the plans you have, access to data, any course corrections you made compared to what was first proposed, any clarifications you have got, those sort of things is what I'm looking for. Max 2 pages, but the deadline is extended to Friday, November 6th, midnight, instead of today. So we've got 2 additional days. And the reason I give you this is because I know, at least I have corresponded with some of you, and especially for those of you who are working with somebody else outside to give you data or something like that, you may need that time. So that's the reason. Do not think of this as something that you have to stress out too much, to be worried too much about. It is good if you have a good plan and you tell me how things would go next. But the most important thing is for me to know where you are, and it will be graded in the sense of saying you look fine and to give you feedback, not graded as when the project is finished graded. Then it will be scrutinized. I will look for quality. I'll look for whatever it is that I have asked for what projects are supposed to do. Okay, so we've taken care of that. You've got 2 additional dates, and that in part has to do with how you might have been late up yesterday. And I don't want that to be another stress for today. So make sure that you do it on Friday, and I don't want any late submissions. Make sure that you tell me where you are and do the best job. And this would help you plan for doing the project itself later on. And by now, we have established everybody who needs to be in a team is in a team. And for the very few exceptions where there is somebody working alone, you have had my permission. So there is no change in mind in that sense. Last time I got a question. We have been saying all along in the syllabus that the week of November 9th is where midterm is. 11th is a holiday. And so we will have the exam on Friday instead, and it will be take home. But I'm going to use Monday's class, if our time allows, all of it, if not half of it, to review so that you would know where you are. The most important thing I want you to know is this is comprehensive in the sense that it will cover the topics we've covered so far. It is coming late in the semester, and my additional goal in addition to assessing is to give you a chance to read through this material and to end in a way. There are very many topics we have covered, and it is nice to get a chance to read through them and have them for yourself. And so the exam will be take home, and we will talk about it more on Monday. That was bullet number 4, and I think this is good. A couple lectures ago, I wrote November 11, not knowing that that was a holiday. If it makes you feel good, November 13 actually happened to be exactly the day we had an exam of this kind for this class last year. So I was surprised to find out how we are on schedule in terms of having things that were tentatively planned and how they panned out later on. So we have a reason to celebrate. The last point I want to tell you, this is good for the entire class, both 475 students and 575 students. EECS, our school, my school, has started something really, really nice this semester. The Industrial Executive Council, or whatever the school has started a session they call, and they run it every 2 weeks, Lunch and Learn with Industry. It's a talk series, and they bring people who are in industry and give a talk. And these talks are really, really awesome. I attended the first, so I didn't attend the last one. And these are people who would talk about their experience in industry, and sometimes they would talk about things that are very generic, and I think something that you would add value, especially when you are looking for jobs and what you can encounter the first time. But if you haven't been working for a while, you may learn. And this way of learning about how people have gone by people who are in industry with a very genuine interest in how education is happening in the school and so on is invaluable. And they started doing this because they want to take advantage of the fact that we are now remote, and so they could have anybody who is on that executive council to give a talk from wherever they are. And so the first 2 I attended, one of the speakers was from Microsoft, and the other one was a junior person who just graduated from ECS a couple of years ago, and then working at SEL. So they had 2 very different nature, but very valuable. So I strongly encourage you to attend this. And all you need to do is go to this place. I'm going to have this link posted later on when we do my post-class announcement later today. I'll send you again, but I really encourage, and it's going to be 50 minutes. You don't have to do anything really. You can have your sandwich, you grab and turn off your camera and hear to them. And when they finish, of course, you can ask questions, then you can turn on your camera and you can stop eating your sandwich. But it is a good way to know. And I had meant to tell you about this earlier, but this is a perfect time. And there is one coming up now on Friday at noon, 12:10. And here is the site where you would go to. Okay. These were the only 2 things that I have on this slide. So I'm going to switch and go to one of these other ones, which is the R session that we will do for the decision trees and random forest. Before I go there, does anybody has any question for me? Okay. If you really wanted to know, I was going to ask the warm-up question for today, how many hours did you sleep yesterday? That was what I was going to ask, but I felt like that was not a good one. So I changed it to Monopoly and Go Fish, or whatever it is that we like to do. Okay, I'm going to stop sharing this. and just go somewhere else now. If I can find it. First, I have to get my R coming here. So this was already posted last time. So what I will do now is, go to the place where we had stopped, and now I'm going to continue. I think this is the RStudio one, and I would share this. And I'm going to look for Brit. Her camera is on. Do you see my screen? Perfect. So I'm going to, what we did last, okay, so what are we doing? We are doing, and we will, again, I have a desire to do 3 things today. I did 1. This is the second, and the third one is start unsupervised learning. So if I don't go line by line very carefully, you have to excuse me. And because you have it, you can go back and look at it. But what are we doing? We are doing decision trees and random forests was the last discussion we have had. And we said some good things about trees, and we say they lack. They lack because they are not very nice in or very high in their accuracy. And so we'll use a bunch of them. Forests would come, and boosting is another one. So forests or random forest was kind of an improvement over bugging. Bugging, random forest, boosting, these are all trees, a whole bunch of them. Bugging would use a collection of them, and we are trying to get averages, right? So we collect some of them and we get average. And soon after that came random forest, and the idea there is now be careful, or you could take advantage of having the trees that you put to average, basically, by making them selective, by reducing the number of predictors you would use in each of these decision trees splits that you would make. And so the idea of random came, the reduction in number of predictors. And boosting is another way of getting more trees, but this time you are adding gradually. And so it's not averaging, you are going after bias and gradually growing trees. And among these 3, random forest is, I have favored it, and you probably have picked up from how I talked about it, is the better one, because boosting would require a lot of tweaking and hyperparameter, tunings and things like that. But random forest does a fairly good job on many cases, and in some cases, it is either the best method to use or be a great building block for other methods to use. This is where we are. And decision trees, whether they are, later on in random forest and boosting, could be used for regression or for classification. So what we did last time was actually look at decision tree when they were used for classification purposes, and there was a car seat and things like that that we looked at. Let me skip that and get to a place where regression tree is used for decision tree is used for a regression problem. And we're going to go to the Massachusetts. We've seen this before. I'm going to clear up this thing. We know the Massachusetts data set. It is about houses and things like that. You remember it. You've seen it a couple of times. So we're going to very quickly look at the decision tree there, some basic function calls and so on, and then we get to random forest and boosting. Okay, I have brought you up to speed now. So I'm going to go to line 48, and let's load it up. We get that. That's great. The reason we do this, and by now you have known, is we are going to write code that's reproducible. And so every time you have random, it's not only in our other things also, random numbers are not really random numbers. Computer science students know it. Really, if you go inside what is happening, it's really a generator. And that generator, just like any other thing, is a function. And so it's pseudo-random generator. It's a field on its own. If you really want to make them look like random, you could do lots of algorithmic issues. But whatever it is that you do, they have a seed. That is what would make something that is generated in one case to be reproducible in another. Otherwise, if you don't have set up that one, then you have a code, you have random stuff in it, and you run it today, you get one result, you run it another day, you get another result. And so to avoid those sort of things, you set a seed. That's basically what is happening in line 49. And I'm sometimes going outside of what really the code is about, but it is not a bad thing to do. Okay, so the Boston data set, you may remember, has got this, different things around it, about 13 predictors or so, and the house price is what eventually would come. And much like anything else, especially when we are going to be using for predicting now, one of the things we would want to do is split our data into training set and test set. So we're going to do that training set from this Boston data set, however many rows it has, we're going to take half of it to do training. And that's what is happening now in line 51. Okay, we have that. And now one of the things that we have loaded up this library, a library called tree in R, and the function is also called tree. So we could build a tree for I think it's the median value or something like that. That's what we want to predict. And we are going to have everything. And we are going to do this in the training set. That's what line 52 is doing. So we have built our tree. We can get some information about the tree. You have it. This is the place where I go fast because you can read this for yourself. But we can also plot the tree. And this is a good reminder for R, where the plot function, depending on what it is taking as a parameter, could do whatever it is that is sensible. In this case, what it is given is a tree. And so it will do a good job drawing a tree. I've told you about this thing when we discussed the theory part of it. And that is, it shows you the terminal nodes, it shows you when decisions have been made, but it also shows you the height of these things when they are branching out. And that has got an implication. The people who did this in R made it convey some information. And that information is how much of the data has been divided up because of that split decision. When it is dividing it up in a significant way, it gets tall. When it's not that big, it gets shorter. That's why the tree is this way. Otherwise, you would have drawn it some other way, right? So that's what it is showing. Additional information is there. You could also get some things on it. You can have the values written down on the decision points and what the values are. That's what this text command did. And now we're going to do cross-validation on it for the purpose of pruning the tree ultimately. You remember, I hope you remember that discussion, why we needed to grow a tree and then come back and prune it to deal with variance and the variance bias trade-off. To get that one right, that's what we would need the cross-validation for. So we can do this and we could get a plot. This is where actually, it's not by design, but something that would be related to what we would do when we start talking about unsupervised learning. And so to get a sense for how improvements you are getting, you can plot something like what we did here. And the B, the parameter, one of these parameters B, tells you to have the lines and then B connected them. But what we are doing here is the predicted value and whatever the thing that is called, I think it's called size is, and that relationship is what is being plotted here. And so the connection with how this is used for unsupervised learning, one variant of them, will be clear when we get there, either today or when we finish it next time. Okay, now we're going to prune this tree, and we are going to, I think there is a parameter called best, which you can question or have a query and learn more about, is where you would tune this to find out what the right value is. We're using cross-validation for doing it. And so we have that, the pruned tree now. And when we plot it, it looks like this one. So the best equals to 5 was trying to get us, so what is pruning? Pruning is, we don't have a bushy tree, so we stop somewhere, and so the terminal nodes would be fewer than if it was grown full. And so this now, when it is 5, you can see has got 5 terminal nodes, and you can see what they are. This one now is not done just like that because we wanted 5 and any 5. It is the best 5 among the things that could come, and that's what the pruning has done. We could write more things around the tree, and we can add the values. And we can now try to use our tree, now that we have built it, this is our model, to predict. And that's what is happening in the line that I will be running now. Line 61, this variable names, this is this kind of codes in the lab that I'm running partly depends on the chapter from the book we are reading. And so these variable names are their choices in some sense. So y hat is kind of trying to relate to how things are denoted in the book when you read it. And so it kind of is nice because now you can see this y hat is meant to show you the y with a hat on it, which is what the book usually does to show predictions. Like you've seen this many times. And so we're going to predict like when linear models or logistic regression, the same function is used, and then you specify whatever it is that is going to define what is to be predicted. What are we using? The tree that we grow on the Boston data set. And we are going now to predict on thing that is not training. That's what prediction would be. So the minus train there would get us the test set, basically, right? So so line 61 is doing that. We get that, so we have our prediction, and now we could start to get values around it. So Boston on the MED-V value, and let's see how it did. We can plot this predicted values against what we did, and we see a value like this. So the y-hat, the predicted values, and the test results are plotted. That's what our plot line did. And you can see that we could get the trend of this by using a AB line, and it looks like it's not doing too bad of a job, the tree that we fitted to model our data set. Okay, this was very much like, if I had time, similar to what we did, decision trees, except now we used it for regression. Much of the discussion we had, this would have applied for a classification problem, which we saw last time. All right. I'm not going to give you a chance to ask me questions because I told you we want to get started with the other topic. But if you have, let me see. You can go also over this one later on in yourself. But are you following me? Can I get one? Whoever. Okay, I got two. Perfect. Let's go to bagging and random forest. Okay. So we've taken care of our trees. We know how to use cross validation. We know how to prune our tree. All of these things, they literally are function calls now in R, and that is exactly what I wanted to avoid. Just to know how to use this is not what I want you. I also want you to know how they work, and so we did spend, the theory part of the lectures for that reason. And this would also help you more or less seamlessly transition when if you were to do things in Python. The ideas are exactly the same. The way people have implemented the details may change, but whatever a tree does, whatever pruning does, whatever it is that we do when it comes to random forest and so on, carry on. So you should, it's not easy always to be bilingual. Some of you would need to stick to one language, for example, for your projects, but it also helps to know how the other one. There are certain things that are easier to do in one language than there are in other languages. I have told you many times, R will be the one I would recommend when it comes to visualization type of things. And if you come to deep learning and what we would learn later on, I would say, okay, maybe this will be a better place where you could use Python. But the code we are going to talk about random forest now will stay in R. So the library for it, just like tree was a library, is called random forest. And these people sometimes are helpful because they've got these libraries and function calls that really don't require you too much to remember them in a way. So there is the library called random forest. Go get it. Is what we will do in line 69. We got that. We do the usual thing because we're dealing with random things, and so we set a seed. This seed, by the way, you could change the value. So I've used 1, 1 again and again. You could use 15 here or 20. The point is that you've got a seed set. Okay. The function, so let's do that. The function to call, just like it was for tree, is called random forest, just like the library is. The function call is also called random forest. We're still going to work with our Boston data set, and we have a library called now bag. We're doing bagging, by the way. So bag Boston, we call it random forest, and the thing that would make it bagging is, let me show you. Let me go to the left, because this one is true. There is a bunch of parameters here. So the data set is Boston. We are using on the training set we have produced, and there is something called mtry. This is how many. Okay, the difference between bagging and random forest is in bagging you have these trees that would use all of your predictors, and then you're going to average them. When it comes to random forest, you're going to use fewer than that, and that is going to be randomly selected, and you've got a chance to choose how many there are. And a good practice would be to use square root of p, I told you. So now the thing that actually made this line call to be a bagging instead of random forest is because we used mtry equals to 13, which is exactly how many predictors you have in the Boston data set. So you've got 560 or something rows. These are all the houses there. But you may remember, if you don't, I'm telling you now, there are 13 predictors there, including MED-V, LSTAT, and things like that. So we're using all of them, is what it means. And that's why it is a bagging, okay? That takes care of line 71. So we have it, and we can get some information about it. So we type the variable name, and so you've got some information that this is a random forest, the formula that's called, and we have, we'll talk about percentage of variance explained, but whatever it means maybe literally how it is. You have got a value for it. It has got a number of trees, 500 trees are grown on this one. And you can imagine, actually, you may not appreciate it, but I just ran it, and there were 500 trees that were grown, and it took almost no time to do it. And so kudos to how fast things are, including our own computers these days. It would have taken a long time some years ago. So it happened on pretty much like as I type within a matter of a few seconds or fewer. Now we have it. Let's do prediction. We do predict much like what we did before. We gave it what the model is, and then we are using it on the test data, and that's why the minus train is there. So that will take care of what we have in line 43. And we can plot and see, and this is what it's showing. The test set versus the y-hat bug, the predicted values. And it's not too bad. And you can see, you can draw a line and see what kind of predictions you are getting with these boosting. No, not boosting, bagging, when we are using all of the predictors. And we can get some idea about the error we are making. And so we can take the y-hat minus the test value we have and square it and take the mean of it. That's a way to get it. And so we have a value. And the reason I'm recording this to show you now is to see if we are going to get any better when we get to random forest. That's one of the reasons. So we have an error, mean square error of 23.59 when we are doing bagging. And you know where I'm setting the up to, right? So I'm going to show you something with bagging, and then by the time we get to random forest, if I'm not improving on this one, then what we learned didn't quite work. So I'm, remember this number so we see how it is improved. Okay, the next line shows us, what does it show? We still are doing random forest with the mtry equals, mtry is a name of the variable, and we can reduce the number of trees. So the first one was the first call we had on line, the first line one was, as much as what the default value, as many trees as it found, but we decided to have the number of trees reduced. That's what we are doing in line 77, and we reduced it to 25. And let's see what happens with that. And we get some tree built. Let's see what prediction it gets. It's here. And let's see the mean of the errors, the mean square error we get out of this one. So it is not too bad when we have reduced the number of trees from that 500 to 20 something. And so this is doing a fairly good job, even with fewer trees, is the conclusion to be made here. Okay, now we are going to make our way to using random forest instead. So we set another seed here, and this time we are going to call it RF. So far we have had bag, and now we're going to use random forest, and the function call is pretty much the same, except now we are saying the mtry equals to 6. And we had 13 is how many we had. And now we're going to, well, square root of 13 would have been 4 or something, I guess. But we are using a little bit higher. So we have a choice. It is up to us to decide what that's actually the only parameter you would need to tweak, by the way, when you do random forest. And some of you would use, I'm sure. There isn't really so much tuning you could do with random forest other than this. How many of your predictors you're going to use for the random split. You do not have the control over how to choose the random splits. The software does, but you get to tell what that number is. And so in this case, we are saying 6. And so let's that happens. And we are predicting on our test set, we get our random forest built and our predictor gotten. Let's see what error we are making this time. We have reduced. Oh, and so we got it down to 19.62. And if we change it another mtry and we made it to 4, we might have gotten another one. This is the place where you would need to do cross validation, when you would need to record your results and then settle for the thing that gives you the best. Okay, last time I talked about one thing that is important, and it's about importance of variables. So among your predictors, which ones are important? They are not equally important. And especially in the context of random forest, it is an important thing to show in addition to your model and how it is doing, because you can evaluate whenever these predictors are used, what their contribution was to the entire model at the end, because some of them are left out by design. That's the workings of random forest. And so the hope is that whatever is left out is going to get a chance to be selected in another run, in another trend, and that's where the improvement is coming from. And so you can, much like leave out one cross validation result is obtained, you can use some of the stat properties there that I pointed out last time to evaluate this and get a plot or some summary at the end. And that function, this whole business, is obtained by calling this variable function called importance, and it's a keyword here. And so let's do that on the tree on the random forest that we just did. Let's see importance of variables, and there we go. And this is really, really nice. So we have 13 of these predictors that are involved in your in your random forest build-up, and they're not equally important. There are some that are important and some that are not important. And so we have a list like this, and the next one would give us a plot. So these are numerical values, and you can see which ones are high and which ones are low, and you can see some of them have got some values that you could see, but the plot is the one that is mostly what is reported and what we will see here that I want to finish off this discussion with. So you can see now, and they are plotted. This is done. I'm trying to do two things at the same time. In addition to showing you which ones are the most important ones, there is also a plot against their mean square error. And so one is in an increasing and the other one is in a decreasing order, is what you, or one of them is about mean square error, about the other one is about node purity. But for now, just focus on the order in which these things are happening. And so RM is how many rooms there are, LStat is the lower stats income of the people, and so on. These are the two most important predictors among the many other ones. So it's probably not too surprising that how many rooms house has is one of the best indicators of how much money it would cost. Everybody would guess that, right? So if you have a house with 5 bedrooms and so on, it will cost higher. But the other, at least for this data set, was where whether the house is in a lower social status or something. That's what the LStat is. These two are the top, and the other ones would follow. Okay, I'm done with random forest. Let's go to boosting, and this one I'm going to be briefer. But let me see if I get another thumbs up here. Whoever thumbs has got. So Magnus has done so many times. So Brittany has done. Okay, so good. I'm going to go boosting. Remember, this is a place where we don't average. We're using many trees, but we do something that sequentially grows. The bad thing, or the downside of this, is there is many things to tweak. In random forest, mtry was the only thing. Here you have more. Otherwise, it would probably be comparable. And if you have the patience, if you have the understanding of what your data set is, it's probably worth it. If not, you would be, I think, comparably okay if you do random forest in reality, in practice when you do it. But again, sometimes all the sweat you can have is worthwhile if something that increases, your accuracy would mean saving a patient, or classifying them correctly. So it probably is worth it for some kind of things. And the library, so we saw tree and random forest were the two libraries that we, had to work with. For boosting, it's called GBM, and this is where they have abbreviation, gradient boosting methods or something like that. That's what it is called. So we need to first get it. Okay, let's get that. We have our seat. Control. This is what I wanted. And now we are going to build a model. And the call would be similar. This is one good thing the people who wrote R have done. The function calls, usually when there are predictions, would follow the same syntax more or less. What you specify in the parameters is what determines what is happening. So GBM is what we're calling. We are going to have the median value of the house predicted. Everybody is taken into account. We are using the training set for the building. And then we have these parameters here, a long list of them. Let me see if I can have it all out. Okay, these are all out. Distribution is Gaussian. This is what makes it boosting. You are deciding how many trees you're going to do because you're going to grow this over residuals and one tree at a time sequentially. And it sounds like crazy that you're going to do with 5,000 trees, but it is not that crazy, and you can afford it. And you will see when I run this how long it will take. And then there is this parameter called interaction days. And I've told you this it's about how many of the variables you are considering. You could do depth 1. It's not unusual to do that. It's not a very good thing, but it's 1. And you could do 2. That means you're doing pairwise kind of interaction between them. And then you can do 4 or 8. Usually, a good practice is to consider powers of 2. 1, 2, 4, 8. I have never seen situations where you would really need to go more than 8. So here is a reasonable choice for this data set. And interaction depth is equal to 4 is what is given here. So let me come back here. So we did do, let's see actually, you just noticed that there is 5,000 trees to grow. The trees are going to be built on residuals, so they are sequential. It's not like in random forest you have grown them all. So it is expected to be a slow process, but let's see. I'm going to be doing it right now. See, it kind of took a little bit, but it is done. All those trees have grown and we have built a model. That's how fast it is. So I can get some summary on it, and here we have. And so because this one is a boosting, because it also has got in its workings, improvements about residuals and so on. One of the things that R automatically does when it says summary, in addition to writing your usual things, by usual I mean it's not the same thing. Whatever it is you get as when you type summary would depend on what the thing that is being queried is. In this case, it is a model. But in addition to giving some basic things about it, in the case of boosting, it also draws the relative influence of variables. And here they are. It's plotted. And these are the same variables we saw last time, the number of rooms, LSTAT, and things like that. And this one is because of how things are displayed, the text sizes here, not all of them are labeled. So the first one is RM, the number of rooms. The second one is LSTAT. That was what our random forest also discovered as the most important variables, and boosting identified them. And if you add them up, the relative influence of this will add up to 100. And so like 40 or I don't know, 30 something percent, I think 33 or 34% of all of this prediction power is coming from these two variables alone. And you can get a sense now, if you were to actually drop some of these, you would probably be just fine. Or you would know now what is contributing the most to these ones. Okay, so that was what our summary gave us, and we could do some more plots. And what I'm going to be plotting now is how this number of rooms and LSTAT would plot. This is called, I think, the plot. When you've got to plot one thing over another, but you will see the influence of this to the overall prediction that we are doing, and that's a nice plot sometimes to see. Here it is, and so you would see, how much of the prediction is a function of the number of rooms. So 4, 5, 6, they are kind of on the same price range, and once you have 7 or 8, it really shoots up, is what it is saying when you reduce the 8 to rooms. And the LSTAT one, I would expect it to go the other way around, because this is where the low stat, when that value is high, the neighborhood or whatever it is high, and so the price of the house will be low. And so let me see if it actually is like that. Yes, it is. And so you can plot them in this fashion. Now we could use this for prediction, and that's what I am going to be doing for the remainder of the lines now. So we're going to be using y hat, like what we have been doing so far. We call this function predict. The model, the test set, how many trees we're going. Let me see this actually. Let me show you all of it. How many trees? 5,000 trees. That is probably all we really need for line 96 to do the prediction. We did, and let's see what error we would get. We do the mean square error, much like what we did before. Here we go. And this was quite an improvement. Well, some improvement compared to our random forest one. It had 19. That's where we stopped. And we got it down to 18. But we did tweak a little bit. So there we have one evidence, at least for the Boston data set, boosting helped us a little bit over random forest when we have chosen things. I did not do the cross validation and finding out what will be a good, depths of interaction and things like that. If you do that, then you would probably end up even better results than this, but it's not, I didn't do that here. Let's see what I have left. This is, I'm in line 98. I just did line 98. I think the depths, yeah, the shrinkage. Okay, here is the place where you could. So there were three things in boosting to tune: the shrinkage, which is how much of a tree is added to the residuals, the interaction depths, and how many trees you would use. So this was 5,000, the interaction depth was 5, and the shrinkage was 0.2, and so we did get another model with these parameters, and let's see what it does on the prediction. We still have predict, and we will do this, and let's see if it got, okay, we did get a little bit of an improvement. This is a place where you say, okay, it's enough now. I don't have to tweak too much to get these other ones. And if I do another shrinkage parameter there, then I might have gotten a different value. Okay, I think this was worthwhile. Let's see if I have 10 minutes. And I'm going to ask you how you're feeling, so at least we can get started with our next topic. But let me see if you have any question for me. Magnus, you can ask.
So the shrinkage there at 0.2, isn't that a little higher than you were talking about?
It is. Well, we could try and see what, let's see. Why don't we live try it? Okay, let's do this and come here. Just keep this number in mind. 18.33 is what we got. I'm going to do this again. We've got this, we've got this, 18 point, so we got it worse. So it must have been something that at least I have played around a little bit, and so 0.2 was not bad. So you're right. I have last time told you about 0.01, 0.1. These are the kind. So 0.1 and less is typically what you would use. And this has, I think, to do with this particular data set and how the first two parameters were so very important that they almost are telling everything. And so a shrinkage value here that is relatively high probably was because of that. The short answer for your very important question is there is no way for us to know. And this is the part that I don't enjoy very much about empirical works, because the best advice I would give is try. Find out what works best. Sometimes if we really, really are careful, and I like that kind of theory, we could have more principled ways to guide people. Sometimes we just don't. And so that's what cross-validation, that would be the closest thing you could come to try out different things, record results, and find out the best way to go about it. But I don't think there is any place where you could say this is the right kind of value. Generally speaking, it's better to grow your tree, if you have the patience and the time, to grow your trees gradually. That's one of the things that the shrinkage parameter does. The whole idea behind boosting is to grow sequentially your trees, and it won't help very much to grow them fast. And so the slower the growth rate is, the better. And the other fortunate thing for us, both here and in random forest, is increasing the number of trees doesn't hurt. We don't have this worry about overfitting, for example. So more trees may slow you down and may not buy you, but it won't hurt you. And that's another thing. So the value was high, but it, as we just saw, helped better than the traditional values for smaller. This is particularly for this data set. It's not going to hold true for others. Any other questions? Okay, well, this walkthrough, of course, helpful. And now this is a time when I can see chat and see you can have more participation. Yes, it was helpful. Okay. All right, let me stop sharing this. And at least let's start with our unsupervised learning discussion. By the way, I have posted what I would think that we would probably be able to get started at least on Blackboard. And I'm okay if we don't get very far today. We'll continue this on Friday. But let's start, okay? This is chapter 10 in the book. And this will be the last thing we would kind of interact with the book. By the book, I mean this book that we are using now. And there are a few topics left where we will leave completely this book and go somewhere else. But they have done a good job on the topics that I have covered, at least the last series of lectures, including what we will be talking about, unsupervised learning now. And so it's good reading place, and some of this material are the way the authors of this book have organized in terms of slides. My slides were slightly different, but this time it is actually the slides of the authors of the book, the way it is. So when we had the machine learning overview, we had a good discussion on supervised learning generally, on unsupervised learning generally, and we brought up why they were needed. What we will do now, and what we will start today and continue on Friday, is look at methods. And so we will kind of remind ourselves what unsupervised learning is and deal with the most important, two of the most important methods or class of methods in unsupervised learning. Okay, so this will be an appetizer, and otherwise you should come very hungry on Friday to continue with what we would do. So what's the difference between supervised learning and unsupervised learning? In supervised learning, we have labels. In unsupervised learning, we don't. We have predictors and response in supervised learning. We had a why. We don't have a why now. And so all we have is predictors, and we are going to find for interesting things, associations between what the predictors are telling us. So the goal is to find find out something interesting about the data set, but there is an even more important goal I want you to remember, and I want you to do it in the context of your project, in the context of your research, in other places. And that is unsupervised learning is also a great way to visualize your data. To get an understanding of what it is saying, the most informative way to visualize your data. It's not just about plotting it in a nice way. It's not about knowing the right R functions, but also to understand in terms of the dimensions of your data and find out an alternative way to get there. So the two methods we would talk, the two classes of methods we would look at is principal components analysis and clustering. And principal components analysis is the one that I would way higher in terms of its ability to show us to visualize. That is, if not an end by itself, an excellent way to get to somewhere else. The other thing I want you to remember, and it is often forgotten, is principal components analysis is also an excellent way to pre-process your data, even when your program was supervised. It's supervised, you end up going to do classification or regression problem to solve, but you've got data that has predictors. And so a good way to pre-process this so that you have manageable things to work with is something that principal components analysis would enable. So that's one class of methods. The other, which also to some degree will help with visualization, is to group your data into clusters. And that is the other major method we would talk about. Group things that are, and I know a good number of you have got projects that to do with clustering. When you know we've got students in the class, we are going to group them based on their interests. We've got market people, and we're going to group them based on how their patterns of things they were pointing. We're astronomers, and we want to group these stars because they, these things belong to the same thing. And that clustering for biology, astronomy, sociology, many other things would actually help us discover a function of a group of cells, a function of a group of stars, a function of a group of people. That's what I mean by a function. And so it's very important. We don't have labels, we're just going to group them. And that's what clustering is. I have 1 minute, so we're not going to get to principal. Okay, the subject for Friday's class is principal components analysis. So you can look forward to that. But let's first just get one thing out of the way. Unsupervised learning is more challenging than supervised learning. Why? Because you don't have labels. Because you don't know what, this is, a car, this is, a truck. That kind of label I don't have. What I have is just pictures, and somebody has taken the pictures and put them on the web, and so I have to go about finding them. Because I don't have labels, and because my problem doesn't have a why, it is ill-defined, mathematically unsatisfying. So it's become subjective. So I'm going to group these things, and I'm going to group them this thing. I'm going to group these other things and call them this other group. Am I right or am I wrong? We actually would come with a way to kind of assess those, but we really don't have a way to that. So it's an ill-defined problem or ill-posed problem, and it is subjective, and that is where the challenge is. But much else in computer science, that could also be turned into an advantage, because now you've got a bunch of things that you can come up with. When you don't have the rules, that's actually sometimes helpful, because now you can come up with your own. You would say, okay, here is the rule I'm making, and I'm justifying it, and then I have a method that's based on this one. Sometimes these are ad hoc, sometimes they are a little careful, but they are something. So let's stop here, and we will start with principal components analysis on Friday, and the slides are posted. So if you'd like to read ahead, that would be great. If not, that should still be okay. But I want everybody to have a good understanding of what PCA, principal components analysis, is, and that's what we will do on Friday. Okay, let me stop here. It's 10 o'clock. I'm going to go through your favorite card and board games and let you know what the tally is. Otherwise, I will see you on Friday. Does anybody have a quick question for me? Did I go slower than I did last time, and you are less angry at me than you were last time? Okay. All right. Okay, I'll see you on Friday.